Okay, good evening, everybody. This is Tom, K3YH, and we're doing a little bit of math review for the technician exam. I was just talking before the recording. Don't sweat the small stuff. You can get up to 9 questions wrong and still pass the test. So if one or two of these things just kind of blows your mind and you figure, I'm just never going to be able to deal with it, that's fine. Just allow yourself a little leeway that you're going to get a few questions wrong, and but you'll still get a license. So let me share my screen and show you what we're going to do. So I'm going to do review for exam, technician review, and review by sub-element. And we'll take a look at sub-element T5D. See if I can figure that out. T5D. Okay. Ohm's law, series and parallel circuits. Okay. So you can see T5D has 14 questions. That's what that says on the bottom. Hopefully you're seeing my screen. You're probably not. Wait a minute. Okay, you should be got it now. You're seeing my technician exam review screen.
Yep.
Thank you. Okay. So T5D, and the first question is T5D01, what formula is used to calculate current? And you see this is 14 questions. So you will get one of these 14 questions, one and only one. And the first 3 questions ask you about the formula used to calculate current in a circuit. And let me show you how to remember this so you don't have to worry about writing down or memorizing equations. So I'm going to flip over to my version of a writing tablet. And I'll spotlight that so everybody can see the big screen. So my version of a writing tablet is actually a pad of paper and a Sharpie. It works for me. It's pretty low tech. Okay, you need to remember this EIR, and I do it inside of a circle. If you can draw this circle, then you know all the formulas you need for Ohm's law. Okay, so draw, put an E on top and then I and R next to each other. It's like the Irish word for Ireland, ear, E-I, I think, I don't know if I pronounce it right. My mother and my wife's mother were both Irish, so whenever I see this, I think of our mothers, and and that reminds me of Ohm's law. So E-I-R inside this magic circle, and that's Ohm's law. So you can just, the simple way to do it is if you cover up one, it tells you the formula for calculating. So if I want to calculate E, it's I times R. Okay, so voltage E equals I times R. If I want to know I, cover that up. So I equals E over R. And if I want to know R, R equals E over I. Okay, so now all you have to do is memorize this circle. Draw this circle. When you go in and take the test, you can't take this circle with you, and you can't write it on the palm of your hand or have a secret decoder ring, but you should be able to remember this long enough to write it down on the, they let you write things on the back of the answer sheet on the in-person test. So and pretty soon you're going to be able to visualize this without writing it down. So now if you get one of those 3 questions that I just showed you, you'll know that the formula for E for voltage is I times R, the formula for current is E divided by R, and the formula for R is E divided by I. And it's always times or divided. There's no pluses or minus. So you see distractors that have plus and minus, and you can ignore those. So let me go back to the questions and show you those three. Okay, so calculating current, and again, I don't have the wheel, but maybe you copied that down. So current is E over R. Okay. Calculating the voltage, E is I times R. And then the last one would be say, okay, so what's resistance? And it's E divided by I. Okay. So you didn't have to memorize any of these equations or do any algebra. Just draw that little EIR magic circle, and that'll give you the answer. Okay, the next question, the next questions, there's about 10 of them, I think. It actually gives you real live circuits and asks you to calculate this. Okay, so I'm going to have 3 amps and what's that say, 90 volts. I have to write that down. I'll switch back to my camera. Okay, so 3 amps and 90 volts. Let's just flip to a blank screen here. My magic tablet. Okay. All right. So for the next like 10 problems, everything's going to look the same. I'm going to have a battery, and then I'm going to have a resistor, and resistor is going to connect back to the battery. Okay. So what happens here? I have voltage on the battery. I'm going to have some resistance here, and I'm going to have current flowing through the circuit. It goes out of the battery, around through the resistor, and back in. We don't worry about positive current and negative and electrons and all this kind of stuff. So the problem at hand said that the voltage is 90 volts, and the current was 3 amperes. Okay, so what I know is the voltage and the current, and what it asks me for is what is R, what's the resistance. Okay, so I do E, I, R. Okay, and I need to know the resistance. So the equation I want to use is R equals E over I. E divided by I. In this case, it's 90 divided by 3 equals 30. 30 what? Anybody know? What's resistance? Shout it out.
Ohms.
Ohms, right. It's not bananas or amps, it's ohms, and the symbol for that is this little omega thing from Greek. Okay, so if I just go back real quick to the screen, actually already checked it for you. What's resistance? 3 amps, 90 volts, 30 ohms. Okay, so here's another one. Now I got 12 volts and 1.5 amperes. Well, what do you know? It's the exact same circuit. Okay, let me see if I can switch back to this. Okay, so now instead of 90 volts, I have, well, that didn't work too well, did it? How's that show up? Not very well. All right, I'm going to just cross that out and say 12 volts. Okay, and then the current is 1.5, so let me cross that out and put 1.5. Same equation, R equals E over I, right? How did I get that? I drew my magic circle, cover up the R, it equals E over I. So in this case, R equals E, which is 12, divided by I, which is 1.5. And so the answer to that equals 8. Okay, go back to share. The question. All right, so 12 volts, current is 1.5. I calculated 8 ohms. Okay, and here's another one that's the same thing. So you got 12 volts and 4 amperes. Okay, so I keep 12 volts, and now this changes to 4 amps. So R equals 12 divided by 4, which is equal to 3 ohms. Okay, so this is the one I'm doing here. And there's your answer, 3 ohms. Okay, so there was 3 problems in a row, but it was exactly the same calculation. I was given the voltage, I'm given the current, and I have to calculate the resistance. I use my magic circle. Resistance is E divided by I, and I solve 3 different ones. 90 volts and 3 amps, 12 volts and 1.5 amps, 12 volts and 4 amps. Okay. All right, I think I've cluttered that up enough. Let's try a new blank piece of paper. Next problem. Now I'm sure they're going to ask us something else. Remember, you're only going to get one of these. You're not going to get all of these questions. You will get one. So, but you have to know how to do all 3 variations. You have to we just figured out how to calculate resistance. The next question is here. It's going to ask me, what's the current? Okay, so what's the current in a circuit with an applied voltage of 120 and a resistance of 80 ohms? Okay. So the first thing is we're going to draw exactly the same picture that we drew before. There's a battery, some kind of voltage on it. It's kind of an ugly battery. I've got a resistor out here, and it connects back to the battery. I got a circuit, okay, and I've got current flowing in that circuit. That's the I. And here's the resistor. So in this case, it tells me that this is 120 volts and the resistance is 80 ohms. Okay, so now I need to calculate the current. Okay, first, E, I, R. Remember my mom, ear, Ireland. Okay, so I need to calculate the current. So I'll just cover up. So current says I equals E divided by R. Okay, so do the math. I've got E is 120 and R is 80. So 120 divided by 80 is 1.5. I equals 120 over 80 equals 1.5. 1.5 what? Bananas, carrots.
Amperes.
I is in amperes, amps. Okay. And I'm sure the next 2 will be just like this. So let's take a look here. Here's the screen, 120, resistance of 80, 1.5 amps. Okay, I'm going to have the same kind of question. They just changed the values, 100 ohms and 200 volts. So if you remember, now you're not looking at the paper and all that other kind of stuff, although you might see it over in the corner of your screen, the the current is going to be the voltage divided by the resistance. And I'll do the whole problem for you, but you can already see the right answer is going to be 2. And let me just go back and we'll calculate it. I'll draw a new picture so it's not so cluttered. Okay, I'll make a simplified battery. That looks like a capacitor, but just believe me that it's a battery in my imagination. Okay, and there's my R. Okay, current, I. Okay, so they tell me that I've got 200 volts and 100 ohms. Okay, magic circle, remember my mom, ear, and my wife's mom. Her name was McEver, which is not Scottish, it's Irish. Okay, so I'm calculating I, so I cover up the I. That tells me that I equals E divided by R equals 200 divided by 100 equals 2 amps, which is what we just said. And it's got one more. The next one, I'm not going to flip the screen. I'm just going to do it for you real quick. Okay. Battery is 240 volts. By the way, some of these circuits will be drawn, you could draw it this way too. In fact, the last one was worded, it says connected across, so just say it's across the 240 volts. Doesn't matter where I put it in the diagram. This is just a schematic, and it just shows that there's a connection from the battery to the resistor and from the resistor back to the battery. So I got 240 volts and 24 ohms. Magic circle. So this is a 2. Hopefully it still doesn't look like a 2. There we go. Okay, so I need to know what's I. There's the current flowing in the circle, in the circuit. And so in this case, I is E divided by R. Okay, I equals E divided by R equals 240 divided by 24 equals 10 amps. That's a lot. This would be like hooking up your toaster oven or something. So let's go back to look at the exam question. Okay, 24 ohms, 240 volts. And read the question. Notice they rearrange. Instead of saying it's 240 and 24, they say it's 24 and 240. So 24 rather is the resistor, that's the ohms, and 240 is the voltage. And so we calculated out that the answer was 10 amperes. All right, let's see, do they have any more like that? Oh, okay. Now, what is the voltage? So that's the third possible combination of things you have to calculate. All right, so just read the parameters. I have 2 ohms and 0.5 amperes. Draw my picture. I'm going to put my resistor back up here because I don't know why I like it there. Okay, and it says 2 ohms, and my current is 0.5 amps. So I'm asking, what's the voltage? EIR, magic circle. I need to know the voltage, E. So E, cover that up, is I times R. Okay, so E equals I times R equals 0.5 times 2 equals 1, what? 1, Orange pit, 1 volt.
Volt.
Got it? All right, let's go back to the screen. Okay, 2 ohms, 0.5 amps, answers 1 volt. So we're going to have the same question here, except different values. So now I got 10 ohms and 1 amp. Okay, this is kind of trivial. It's, you know, so it's I times R, so it'll be 10 volts, but I'll do the example. Battery, resistor. Okay, I is 1 amp, 10 ohms, okay. So I want to know what's E, what's the voltage, so it's I times R. So E equals I times R equals 1 times 10 equals 10 volts. Okay, and we selected that answer. So got a couple more here. All right. Same question. What's the voltage? But now it's a 10 ohm resistor and 2 amperes. Okay. So I'll just try to use the same picture for that if that's okay. So I still got a 10 ohm resistor, but now I'm going to be using current of 2 amps. I think it should be fairly obvious that it'll be twice as much, but let's go ahead and do it. So E equals I times R. Remember, cover up the E, it's I times R, equals 2 times 10 equals 20 volts. Ten ohms, 2 amperes, answered 20 volts. Let's see what the next 2 questions are. Okay, so this is just a word problem. What type of circuit is DC current the same through all the components? Well, that would be a series circuit. And then what type of circuit is voltage the same across all components? And that would be a parallel circuit. Now, the circuits I've drawn here are kind of trivial, so they actually exhibit both. In this case, the current goes through the battery and the resistor and all the wire, so it's a series circuit. And I drew it a little earlier with it's more representative here, that you can see that the battery and the resistor are also in parallel. So again, that's kind of a trivial version where it's both. But let me give you 2 examples, or an example of each is what I'm really saying. Okay, so let's say I had a circuit where I had a battery over here, and I have several resistors like this, and then it goes back to the battery. So the I goes through all the components. It's the same through each of the resistors and the battery. So this would be a series circuit. Okay. Now let's say I had a circuit, and again, I know this looks like a capacitor, but just imagine it's a battery. Now I'm going to put some resistors like this. Okay, so there's I that comes out of here, but now some of that current goes here, and some of that current goes here, and some of that current goes here. So the current through these three resistors is different. It's not the same current because it's got to be divided up, and how it divides up is according to the value of the resistors. But the voltage is the same. So the voltage is here on the battery, then it's the same voltage across this component, and the same voltage on this component, and the same voltage on this component, because you can see they're all actually connected to the battery. So the top of this, and the top of this, and the top of this are all the same voltage as the battery. So, and again, physically looking at it, you can clearly see that these are in parallel. So this is parallel, and that says that the same voltage is across each component. And this series says that the current is the same through each component. So, okay, that's the story of that. So that gives you the T5D question. You've just seen the three possible ways that the calculations that they would ask you for, and then a couple of word problems or formula statements. But once you go back to the magic circle, other than knowing series and parallel, that answers all your questions. And like the most important part is you don't have to remember a bunch of formulas. You've just got this thing right here to tell you how to do the calculation. Okay. Let me switch back to sharing. Trying to get my, I'm afraid that the side window that has all the participants might have been blocking part of the video and the recording. Roll, did you join us? I don't see him. All right. Okay, the next thing I want to look at is calculations of power. And that's covered in the questions in section T5C. So go to subelement T5C, and this is kind of a hodgepodge. T5C has questions like, okay, what describes the ability to store energy in an electric field? That would be capacitance. The unit of capacitance is the farad. I'm just going through these quick because I don't really want to review these. I want to review the math. Storing energy in a magnetic field is inductance. The unit of inductance is the Henry. The unit of impedance is the ohm. I'm trying to get up to C8. Okay, so what's the formula used to calculate electrical power in a DC circuit? Okay, so once again, I suggest that you think about the pie chart. Switch to my camera here. I'm going to draw the same circle, but now we're just going to have to remember P, I, E. Okay, so for Ohm's law, remember I had that magic circle, and I said, remember my mother and my mother-in-law with their Irish heritage. But in this case, for power, you've got the pie chart. So P is power. And then you've got I and E, which are current and voltage. So same story as before. If you want to calculate one of these three values, cover up the one you don't know, and that gives you the formula. So power is equal to I times E. The current times the voltage gives you the power. So we'll switch back to the question. Okay, what's the formula used to calculate electric power in a DC circuit? And so here's the answer, the first one. Power equals I times E. Actually spells out the old pi there. Okay. And remember, everything for power in Ohm's law is multiply and divide. So you can rule out C and D right away. There's no pluses and minuses. You're multiplying in this case. Power is I times E, and you knew that from the pie chart. So the next one, see, 8, 9, 10, there's 4 possible questions here. This one, they ask you to calculate power. Okay. So how much power is delivered by 13.8 volts DC, which would be your typical automobile voltage coming from your battery, and a current of 10 amperes, which would be a typical current for a mobile radio, like a VHF 2 meter and 70 centimeter radio mounted in a vehicle. So let's look at what that looks like and draw a picture. You don't have to draw a picture, but I'm going to do something. So let's just draw the circuit again where I've got a battery and it's 13.8 volts and it's connected to a load, and sometimes you'll see this drawn as sort of a box that says load, or let's take that out of the picture. We can just oversimplify it here and make it a resistor. Okay, and they tell me that the current is going to be 10 amps. Now you don't need to do all this because you're not trying, it's not like Ohm's law where it says calculate the resistance. You could, it would be 1.38 ohms, but what it asks you is what's the power in this circuit. So I got 13.8 volts and 10 amps. So remember, I want power. So power is I times E, okay? So P equals I times E, which equals 10 times 13.8, which equals 138 watt. Made it too easy, right? It's 138 watts. Okay. So I used my pie chart and said, okay, I need P, so it's I times E, and I got 13.8 is the E, 10 amps is the I, so I'm consuming 138 watts. So 13.8, a current of 10 amperes, 138 watts. So here I got the same question with different values. How much power if you have 12 volts and 2.5 amps? Okay, so in this case, the answer will be 30 because it's 12 times 2.5. But let me show you how I got that. Okay, P, I, E, pie chart. Right after this class, I'm going up to the store and getting a pie. I can't stand it. Okay, so in this case, I'm not going to even draw the circuit. So P equals I times E. And the question said I have 12 volts. Whoops, we do current first. 2.5 amps, doesn't really matter, times 12 volts. And so that equals 30 watts. Okay, so again, this would represent some kind of source, a battery of 12 volts, and some kind of load That's what we call whatever it is that's consuming power. We call that a load. Something that consumes power. We talk about on an antenna. We connect a dummy load to use up the power. Okay. So, and the current, of course, was 2.5. Okay, so we go back to the screen. 12 volts, 2.5 amps, 30 watts. And then there's one more. I think this is the harder one. Yeah. Okay, so now they throw you a curve, so to speak. How much current is required to deliver 120 watts at 12 volts? Okay. Now, why would you care to know this? Well, that would tell you what size wire you need to use. Because you're saying, okay, I've got a thing and it consumes 120 watts and I've got a 12 volt supply. So I want to know the current so that I can make sure I use wire that's appropriately sized for that current. Okay, so here's my supply, 12 volts, and I got a load and it's using 120 watts. So I want to know what's the current. So that makes, when I get the current calculated, then I can go to my wire tables and see what gauge wire, what size wire I need to handle that current without melting it, essentially. Okay, so pie chart, PIE. Okay, so what do I know? I know the power in watts, and I know the voltage, 12 volts. So what I'm trying to find is the current. So I'll just cover that up, and it says current, I, is equal to P divided by E. Okay, so the I is equal to P divided by E, and that is 120 divided by 12 equals 10 amperes. And there's the right answer, 10 amps. So in two of the questions, and you might not get any of these because there were these other questions about capacitors and inductors and Henrys and things like that. But if you get a power question, they'll either ask you to calculate P or in this case, I. And like I said, these are real world problems because these are the kind of things that you would want to figure out if you're doing an installation. Okay, the next thing I want to cover is some antenna questions. And let's see, it's T9A. Oops. T9 antennas and feed lines. And so here's T9A. So you see this again, this is a real smorgasbord of possible questions that you could get. They might ask you about polarization or gain or types of antennas or beam antennas or whatever. So let's just take a look at the two that we're interested in, and it's T9A8. Oops. T9A8. Okay. So what's the approximate length in inches of a quarter wavelength vertical antenna for 146 megahertz? So there's a little box. Let me get my book. Antennas were section, chapter 5. No. Chapter 4. All right, so just take a look at the question. I want to know inches. How long is a quarter wavelength vertical antenna for 146 megahertz? Okay, so let's take a look at the book, for example. And this box is on page, my camera isn't very cooperative here. This is on page 4-13. How do you calculate an antenna? Oh, somebody asked me why PIE isn't arranged that. I don't know why, it's just pi. I just write it counterclockwise. I spell out pi. Okay, so there's some what we call rules of thumb that we use to calculate antenna lengths, and they're close enough. There's a lot of discussion about what the number should be and how accurate it is and so forth. But for purposes of taking the test, we don't really care. An antenna for a dipole, which is a half wavelength, the length in feet is equal to 468 divided by the frequency in megahertz. And for a quarter wave antenna, which is what they ask us to calculate here, it's half of that. So a dipole is a half wavelength long, and a quarter wave vertical is half of that. So that would be, it's down here on the bottom of the page where it says for a ground plane that is half of a dipole, that length would be 234 divided by the frequency in megahertz. So it's really easy to remember. 468 for a dipole and 234 for a quarter wave vertical. Okay, 468 for the dipole, and the dipole is a half wavelength, and half of that is a quarter wave, and that would be 234. I'll draw a little picture here. Oh, hang on, I dropped my pen. Okay, so a dipole, your classic dipole is a thing hanging up in two trees, and remember the wavelength is symbolized by the Greek letter lambda, and the length of this is lambda over 2. So it's a half a wavelength. So it depends on the frequency. Remember, the frequency wavelength is equal to 300 divided by f, if f is in megahertz. Okay, so that's not 100% accurate for actually calculating the antenna. So we've got a new rule of thumb, and it says the length, by the way, of course, that's meters. The length in feet is equal to 468 divided by f in megahertz. That's your half wave antenna. Now, a quarter wave vertical antenna is mounted on the ground theoretically, and of course it's got this reflected imaginary other half which is down inside the ground, and so this length here is lambda over 4, and you can see lambda over 4 is half of lambda over 2. So for this one, the length is equal to 234 divided by f. Okay. So now you got Yeah, a little bit of math to do here. And by the way, I don't know if I've talked about this before. If you don't have a calculator and you want to get one that you can use as we go further through the classes, I suggest this TI-30XA. You can get it at Walmart or Amazon for 10 or 12 bucks. And this is what I use, and it does way more than enough for what we need to do here. So the problem they give us, we're using, it says I got a quarter wave vertical antenna for 146 megahertz. So let me flip the page and do that one. Okay, so here's my antenna, and it's lambda over 4, or a quarter wave vertical. Pretty standard, and it's for 146 megahertz. Okay, so the rule of thumb is that the length in feet is equal to 234 divided by f in megahertz equals 234 divided by 146. Okay, and so we'll just do 234 divided by 146, and you can see that equals, with all the numbers up after the decimal point, it equals about 1.6 feet. Okay, so the question asks you what the length is in inches. So I have to multiply that times 12, and that tells me it's about 19 inches. So this 146 is in the 2-meter band. If you think, well, wait a minute, 300 divided by 146 is 2.1 something or whatever. Yeah, well, we call it the 2-meter band. We're always off a little bit. And a quarter wave vertical in a 2-meter band is about 19 inches tall. So let's go back to the okay, what's the approximate length in inches of a quarter wavelength vertical antenna for 146 megahertz? And it's 19. Okay, if I were you, I would just memorize this, right? It's 19 inches. Because you can do the math, but you should know this anyway. You've kind of got this eyeballed that it's about 1.5 feet, 19 inches. There's other ways you could do it if you remember how long a meter is, and I'll show you that in a minute when we do the other question. Okay. Did anybody have any questions about that before I go on? Shout them out. Okay. All right, so what's the approximate length in inches of a half wavelength? Get this, half wavelength, 6-meter dipole antenna. Okay. And we'll do a bunch of calculating here, and then I'll show you a real easy way to solve this.
Could you show the question again?
I wasn't sharing, was I?
No.
Sorry. Well, I'm not sorry, but I'll fix it. Okay. Let me grab a slug of water here too. Okay. So what's the approximate length in inches of a half wavelength 6-meter dipole antenna? Okay, so I've got a dipole. It's a half wavelength long. How many inches? All right, got it. Okay, so let's go back to this thing here, there's my dipole, and it's a half wavelength long. And of course, the rule of thumb for that is to take 468 divided by the frequency in megahertz. You can ignore that thing over there. Okay, so there's a couple issues here, and somebody asked me this the other night. It says, well, what's the frequency for 6 meters? 6 meters is approximately 50 megahertz. If you use this equation here, let's do that first. And so now there's another magic circle here. You're going to have wavelength and frequency and 300. Okay, so the 300 is a constant, which is the speed of light. And you know, you're thinking, well, wait a minute, but it's 30 million or something like that. But if you use megahertz in frequency, then you can put 300 here. So the wavelength in meters is equal to 300 divided by the frequency in megahertz. So that has to be here. And this has to be meters. So this isn't your antenna. This is your actual true wavelength, okay? So using this, lambda, no, I know I need to know F. I'm sorry. F equals 300 divided by lambda. So I have 300 divided by 6 meters equals about 50 megahertz. Okay, so the 6 meter band is 50 megahertz. Okay, so now I'm going to do the 468 thing. So the length in inches, the length in feet is equal to 468 divided by 50. We'll do that exactly just for the heck of it. Equals 9.36 feet. And now your head's spinning. Like, geez, Tom, you had 6 meters and 300 and 9 point, and that's feet. How do I get it? And oh, by the way, they want the answer in inches. So I got to multiply that times 12. So if you got all that, it's 112 inches. Okay, so let me go over what I did again. First off, I had to figure out what's the frequency for 6 meters. So I used this circle, and it said that to calculate the frequency, I divide 300 by the wavelength in meters. So I divided 300 by 6 meters, and I got 50 megahertz. Okay, now that's the frequency, but what I want to know is how long this dipole is. So for a dipole or half wavelength antenna, approximately, it's a rule of thumb, the length is 468 divided by the frequency in megahertz. 468 divided by 50, 9.36 feet, 112 inches. Okay? So, on the other hand, if the wavelength is 6 meters, then a half wavelength is going to be 3 meters. And 1 meter is about 40 inches, a little bit less. So a half wavelength at 6 meters is approximately 120 inches. A little less, because this is really like 39, right? So a little bit less. And then, of course, there's a rule of thumb. The antenna length is not exactly a half wavelength, but Just by taking a half of 6 meters and converting it to inches, I got 120 inches. Now remember, the calculated is 112, but using only counting on 5 fingers. Well, I needed 2 hands. I took 6 and then counted a half. So I got 120 inches. So let's look back at the question for a minute. All right, so the approximate length in inches of a half wavelength 6 meter dipole antenna. So again, if I just take, by the way, we calculated the right answer is 112. Okay. But if I took 6 and divided it in half and said, okay, a half wavelength is 3 meters, and 3 meters is about 120 inches, you can see that the answer 112 is the only one that's even close. So again, you don't have to do the math. If you do the math 2 or 3 times on your own and convince yourself that that's the right answer, when you get to this, you'll look at this and say, okay, let me see. Half of 6 meters is 3 meters. It's about 120 inches. Yep, it's this one. So that's how I would attack that problem. I would just think half wavelength, half wavelength of 6 would be 3. That's about 120 inches, close enough to this answer. When you look up at an antenna hanging between a couple of trees, that's how you eyeball it and say, oh, that looks like a 20-meter dipole, because it looks like it's about 30 feet long. So if you do the math, then you've got to remember, you've got to convert 6 meters is 50 megahertz, divide 468 by 50. That'll give you feet. Convert that to inches. I'll show you that again. Okay, the first thing I did is converted 6 meters to frequency, and that's 50 megahertz. Or you just remember that, because pretty soon you'll be familiar with all the bands and you know what frequency is which band in meters. So the length in feet using the rule of thumb is 468 divided by 50, which is about 9.36 feet, which converts to 112 inches. All right. Let's look at how am I doing on time. Oh, pretty good. I'll do dB, which is under T5. T5B. Okay, so T5B, we'll look at this for the rest of the night here, but I'm going to start at the end. The other part is math for electronics, conversion of electrical units. This is where you do the milli, micro, kilo, mega, where you use the metric prefixes, and we'll do that after I do dB. So the decibels, hopefully, you're not seeing it, I'm sorry. I thought I clicked on share. All right, let's start over. If I forget to share, you can shout out, say, hey, you forgot to share, Tom. Okay, so see here, T5B could include math for electronics and conversion of electrical units. So that's the metric prefixes with kilo, mega, micro, milli, nano, and then decibels is part. So you'll get one of these questions. If you're lucky, you'll get one that says, how much is twice the power? It's 3 dB, and you know that off the top of your head. So let's take a look at those. I'll skip these for now, I'll come back to them. I'm going to B09. Okay, what decibel value most closely represents a power increase from 5 watts to 10 watts? Okay, let's go back to the paper. I'm going to use the L word, but I'm not going to write it down or do any calculations. All this decibel stuff is power ratios, and it's based on logarithms. There was a time when people couldn't multiply and divide because they hadn't invented the zero. And among other things, they came up with logarithms which allowed them to um, calculate the multiple summations or multiplication of two numbers. And basically, the multiplication of two numbers is equivalent to adding their logarithms. So people knew how to add and subtract. And there's this big story about counting beans on a table, and that's the origin of the word bean counter. I won't go there. Um, and so people could add and subtract, so therefore they added and subtract logarithms to develop multiplication. When I was in college, we didn't have these. So we had a book which had tables of logarithms, and you had to go into the table and find the logarithm of a number to use for calculations, and then you'd use the table to convert the logarithm back to a number. And there was a whole science, or not a science, but a learning process to that. Now we just don't care about that because we got a calculator. And you don't even care about that because you know that 3 dB means 2 times. So if I go from 5 watts to 10 watts, then that represents a increase of 2 times. 5 to 10 is 2 times, and the dB equivalent of that is 3 dB. What's an example? An example, we've done this with antennas. You might have a directional antenna, and they show these little charts where it's got maybe a lobe in the back, and then there's some other side lobes perhaps, and they'll say that the front to back ratio, or the gain of the antenna, is like 2 times, but they always express it in the dB. It's 3 dB. So this antenna has a 3 dB gain over perhaps a dipole. This would be like a little beam antenna that focuses the energy in one direction. So we get double the power is equivalent to 3 dB. And if I double it again, so if I have 2 times 2, so 2 times 2 times equals 4 times, that's equivalent of 3 dB plus 3 dB, which equals 6 dB. So multiplying the gain or the amplification in the actual number of the gain is equivalent. Then to do the equivalent with logarithms, you add them. So if I get 4 times the amplification, that's 6 dB of gain. And then the other one is where I have a gain of 10 times, and that represents, or 10 dB represents that. So these are the ones you have to know. Let me go back and look at the questions again, make sure I got them all covered. Share. Okay, so a power increase from 5 watts to 10 watts is 2 times, which is 3 dB. And the next one says, okay, here's a decibel value most closely represents a power decrease from 12 watts to 3 watts. Okay, so if it's a decrease, it's minus. And just what I showed you, I showed an increase where it was 12 divided by 3 is a decrease equivalent to 4 times. And as I said, 4 times is 6 dB. And again, since it's a decrease, you use minus dB. And then the last one, what if you increase from 20 to 200? That's 10 times, and that's 10 dB. Okay, so what do you have to remember? 3 dB equals 2 times. If you multiply the gain on one side, you add it on the other side. So 6 dB equals 4 times. Decrease is minus. So for the particular question, it's not really 4 times, it's actually 1/4, and that's minus 6 dB. And then 10 dB is 10 times. Okay, so if you're familiar with exponents, you know why this is. If you're not, just remember it. If it's 4 times, it's 6 dB. If it's 1/4, it's minus 6 dB. Same up here. If it's 2 times, it's 3 dB. If it's 1/2, then it's minus 3 dB. Okay. 3D, I've got my grandson to memorize this. I'm going to give him a test on Saturday. It's his 8th birthday. So 3 dB, how much? See if he comes up with it. I'll let you know. All right. Roll, did you join? Are you here? Wow. He's going to make me do the other thing. All right, let's go back to the beginning. I'm just going to go reset everything. Review, technician. Oh, review progress, clear data. Okay. Because it might skip questions. So I go back to T5, right? T5B, math for electronics. Okay. So here's where I've got all my conversions, where I've got millis to amps, for example. So let me just expound on that a minute. Oh, I didn't share. Start over. Okay, so I'm in T5B, and there'll be a whole bunch of these questions about doing conversion using metric prefixes. So for example, here's the question where it wants you to convert amperes to milliamperes. Okay. So, and milli represents 1/1000th. Okay, so let's flip back to my pad. And so if I have one of something, okay, and then the next, going to fractional sizes, I can have 0.001 of something, and that's called a milli. It's 1/1000th. So if I've got 1,000 milli somethings, that equals to one something. If I take a banana and I slice it into 1,000 slices, then each one is a milli banana, and put them all back together, and I'll have one banana. So and then the next level down would be 0.0000. I get the right number? 1, which is a micro, which is 1 millionth. And then I got a 0.000000001, which is a nano, and that's 1 trillionth. I'm sorry, billionth, right? I'm using the word problem. You don't have to worry about that. And then finally, I've got and that's a pico, and that's a trillionth. Or in scientific or in engineering notation or scientific, that would be 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, and 10 to the minus 12. So just look at this one because that's what the question talks about. So again, if I have, there'll be a milli something means it's 1,000th. So therefore, it takes 1,000 millis to make one of the unit, or 1,000 slices of banana to make one banana. In this case, it would be 1,000,000 or a millionth, and so forth and so on. So you basically, if I said I've got one and I need to express it in millis, then I would add 3 zeros, 10 to the minus 3. If I've got something and I want to express it in micros, then I have to put 6 zeros. So what do they ask you? 1.5 amperes to convert it to milliamperes, it's 1,000. So I have to say it's 1.5 times 1,000 milliamperes, or 1500. That's not a comma there. Let me put this 1500. Okay, so let me go back to the question. And this is fairly straightforward because there's 1,000 milliamperes in 1 ampere. So there will be 1,500, which one? That one. 1,500 milliamperes equals 1.5 amperes. All right, let's try the next one. All right, so this goes the other way. Let me just go, let's do some more. Here we go, micro. Okay, what is equal to 1 microvolt? Okay, let's take a look at that. Remember I did micro, and I said a micro, there's 1,000,000 micros in one of something. So if I have 1 microvolt, that is 1,000,000th of a volt. Okay, so what is equal to 1 microvolt? And it's 1/1,000,000th of a volt. So kind of associate this. Micro means a millionth. Milli, 1,000th. Or 10 to the minus 3. A micro is 10 to the minus 6. Okay, 500 milliwatts. Okay, so milli means 1,000th, right? So if I have 500 thousandths, that's the same as 0.5. So I'm back here again. I've got milli. Now let me show it. So I have 500 milliwatts. Then we use a little m for milli. Okay. So 500 milliwatts means that's 500 over 1,000 watts. The milli means it's a thousandth, which equals 0.5. Now, another way we talked about this the other day is if I was going from milliwatts to watts, remember, there's milliwatts, so watts is up the scale, so to speak. So in order to go from milliwatts to watts, I basically have to move my decimal point 3 places to the left. So instead of 500 milliwatts, it would be 1, 2, 3 to the left, which translates to 0.5 watts. So as you're going from one quantity to a larger unit, you move your decimal point to the left. If you're going from the larger unit to the smaller unit, you move your decimal point back to the right. All right, let's see what's next. Okay, what's equal to 3,000 milliamperes? Okay, so we're going to convert it. The choices are all amperes. So I'm going to go from 3,000 milliamperes, which means represents 3,000 thousandths. So the answer would be 3 amperes. And you could also look at it as, since I'm going from milliamps to amps, I move my decimal point to the left 3 places. So I go bump, bump, bump. And so 3,000 milliamperes would be 3 amperes. We'll skip out for now. Let me see if I got. Okay, this one will blow your mind. We'll have to do this one on paper. Okay. So you're going from it wants you to go from picofarads to microfarads. By the way, farads are units of capacitance. Okay. So from picofarads to microfarads is 6 places. Okay, picos are a trillionth or 10 to the minus 12th, and micros are a millionth or 10 to the minus 6. So previously we went from milli to units and it was a jump of 3 decimal places. Now I've got to move it 3 decimal places plus 3 decimal places to go from pico to micro. Okay, so I have 1,000,000 picofarads. I'll just do this. And by the way, you'll hear us call this puffs, picofarads. And I want to go to, I should have drawn this differently. Let me do this down here. I'm going to 1,000,000 picofarads. And I want to go up to microfarads. For micro, we use a Greek letter mu. In between here would be nanofarads. Okay, so I'm going from picofarads to microfarads. So It's 3 places to go to nano and another 3 places to go to micro. So I'd move the decimal point. So here, this would be 1,000 nanofarads. I move the decimal point over 3 places. And then to go from here to here, I'd move that decimal point 3 places again, and that's 1 microfarad. So, and again, remember we talked about that this is 10 to the minus 6, and this is 10 to the minus 12, and this is 10 to the minus 9. So I'm moving the decimal place the decimal point a total of 6 places to the left as I go up to bigger units. So the answer here would be that a million picofarads is equal to 1 microfarad. Okay. And again, if you just, looking at the word problem, you say, okay, I'm going from picofarads, you have to know the order of everything. So microfarads are up the chain, so to speak, up the ladder, 2 steps. So you've got to move your decimal point 6 to the left, and that gives you 1 microfarad. Okay, what's the answer to this? Everybody knows it's 3. All right. So let me go back and do the ones that I skipped. I think I have to go back. Hopefully, yeah, here we go. Okay, now let's look at the other side of the scale. So I've got 1,500,000 hertz. This is, of course, a frequency. And now they mess with you big time because they give you 3 different possibilities. Like, okay, is it 1,500 kilohertz? Is it 1,500 megahertz? Is it 15 gigahertz? And then they throw this one as 150 kilohertz. So now it's not so straightforward. You got to figure out what each one is and sort of test it. So let's look at it generally. So remember I had somethings, and let's quit calling them somethings or bananas. Let's call them 1 hertz. Okay, and then if I have a kilohertz, is 1,000 hertz, and a megahertz is 1,000,000 hertz. So again, this is 10. Remember I did before, I did the exponent of 10 to the minus 3. Well, now it's 10 to the 3. That's 1,000. And then this is 10 to the 6. That's 1,000,000. And then a gigahertz is a billion. And then there's terahertz, which is a trillion. Good enough. So this is 9 and 10 to the 12. So we went down. Remember, we had hertz, or not, we had like farads. So then we went milli. So the mirror image, milli and kilo, micro and mega, nano and giga, and then pico, which would correspond to tera. So going this way was 10 to the minus 3, 10 to the minus 6, and it would be 0.001, et cetera, et cetera, et cetera. Okay, so 1 kilohertz is 1,000 hertz. And 1 megahertz is 1 million hertz, and so forth up the line. So when I'm changing from hertz to kilohertz, I have to move my decimal point again as I'm going up. I have to move my decimal point to the left 3 places. Okay. So, and then convert it to megahertz, I move it to the left 6 places and so forth. So the question asks me, what's 1,500,000 hertz? Okay, so if I move the decimal point from here over 3 places, then that would be 1500 kilohertz. And I move it 3 more, and that would be 1.5 megahertz. And at this point, I think I've solved the problem. Let me go back to the question. And let's just remember this. Okay, so the answer is probably going to be either 1500 kilohertz or 1.5 megahertz. I go up to
We're not seeing the question.
What's that?
We're not seeing the question.
Yeah, I'm going to it now.
Oh, okay, sorry.
I'm slow sharing. I have to click like 3 buttons to share. Are you seeing it now?
I see your calendar.
I clicked on the wrong thing. There we go. Okay, so the possible choices I had was 1500 kilohertz or 1.5 megahertz. So 1500 kilohertz is the right answer. And again, do the little mental exercise what I did. So I move the decimal point 3 to the left, and that gives me 1500 kilohertz, which is the answer there. If I moved it 3 more, it would be 1.5 megahertz, which is not one of the choices. And it's not 150. That doesn't calculate. And of course, this is too big. It would be, if I moved it, it'd be like 0.015 gigahertz. So to do this one, you got to sort of test it. Say, all right, if I convert this to kilohertz, it's 1500 kilohertz. Okay, that looks like the right answer. If I convert it to megahertz, it's 1.5 megahertz, and that's not one of the choices. So you know that's probably the right one. Okay, this one's pretty straightforward. 1 kilovolt is 1,000 volts. Okay, if you were doing the decimal point moving thing, let me just show you that on paper. Okay, so I've got 1 kV. If I could, and now I'm going from kilovolts, here it's hertz, down to units. So in this case, I have to move the decimal point to the right 3 places because I'm going down. So from this unit to this unit, I move the decimal point to the right. So 1, so I'd have to add 3 places to get 1 kilovolt is equal to 1,000 volts. And the next one, all right, so here you go again. Oh, okay, we only have to convert it to kilohertz. Okay, so 3.525 megahertz converted to kilohertz. Okay. Go back. So I'm going from megahertz to kilohertz, which means I have to add zeros. I'm going down, so I move the decimal point to the right. Okay, so the question was, and we'll mess with you all the time with this stuff. We'll say megahertz and kilohertz in the same breath. So I've got 3.525 megahertz. By the way, that's in the 80 meter band. Okay, and I say, okay, what's this in kilohertz? So I have to move the decimal point to the right, so it's 35. 25 kilohertz. So I move this over to the right 3 places to go from megahertz to kilohertz. Or add 3 zero or multiply it by 1,000 because I'm going from megahertz. It's a factor of 1,000. This is thousands of hertz. This is millions of hertz. Back to the question. So 3.525 megahertz. Move the decimal point to the right 3 places. It's 3525 kilohertz. Okay, we did that already. And this was 10 dB. Oh, here we go, one more. Okay, so I'm going 28,400 kilohertz, and it obviously 28,400 kilohertz cannot also be 28,400 kilohertz. So you throw this one out. So it's asking you to take kilohertz to megahertz. And, again, just visualizing it from kilohertz to megahertz, you're going to divide this by 1,000. So it'll be 28.4 will be the right answer right there. Megahertz are a larger quantity in kilohertz. So you take this and divide it by 1,000 to get megahertz. If you're going from kilohertz to hertz, you would multiply it by 1,000 or add 3 zeros. And here I'm going from megahertz to gigahertz, so that's going up. So I have to divide it or move the decimal point to the left, so it's 2.425 gigahertz. Let me show. I'm not using the exact, what was that number? 2425. So 2425 megahertz would be 2.425 gigahertz. So I move that decimal point to the left because I'm going up. If I was coming down, it would be 2425000. So you can see this is microwave frequency. This is approximately the frequency of your microwave oven that you use to heat up food in the kitchen, as a matter of fact. This is a frequency we use for radar transmitters and stuff I used to do at work. A little bit higher. Switch back to, switch back to this. Okay, so that covers pretty much anything with a number on the test. And as it turns out, if you didn't know any of these things that I went over tonight, you would only miss 3 questions, and you can miss up to 9. So, I'll say again what I said at the beginning. I want you to learn these things. It's really important to be able to convert kilohertz to megahertz or milliamps to amps, and eventually people will be talking about these things when you're at a club meeting or doing some kind of operating exercise. But what if somebody says, "What frequency is on?" He says 14,240. You're kind of like, well, what does that mean? Well, what he means is kilohertz. It's 14,240 kilohertz, which is on the 20-meter band. And so then you might ask, so what is that? And he'll say, well, it's 14 megahertz. And now you're kind of like, okay, well, so which is it? And so you'll get more familiar with it as time goes on when you're actually operating. You've got two phases here. One is you want to pass the test so that you can get your license so that then you can start operating and getting on the air. And um, and then you'll get more familiar as time goes on. So I want to stress that it's important, but it's not so important that you get hung up on it and fail the test. And again, if you blew off all of this stuff that I talked about tonight and knew everything else, you'd still pass the test with 3 or 4 to spare. So that's kind of how it turns out. I've kind of got to balance out what you'd like to know, what you really should know eventually, and what is it going to take to pass the exam. Now, when you get to the general, we're going to do more of this stuff, and it'll be a little bit more complicated, which means you really should start learning it at some point as you get practicing with when you have a license. Okay, any questions? Speak up,
Yeah.
chat, holler, raise your hand. Dinah,
Hi. Can you hear me okay?
I can, yes.
Okay. So I think I wrote it down wrong. I'm trying to get if you go up on the chart of, the metric units, you move the decimal
To
to
the
the
left,
left.
yes,
And then if you go down,
to the right,
you add zeros, or you move the decimal to the right.
yes.
Okay,
So when you
thanks.
go up, you're basically dividing. You took 1,000 of something and you divided it and you made one. When you go down, you're multiplying it. You're taking one of something and making it into 1,000 or 1,000,000 or 1,000,000,000 or whatever. Someone asked on the chat, how accurate does your antenna length need to be for transmitting? Um, so the better the better your length is, the better you'll match up impedance wise. Remember we talked about standing wave ratio or SWR, and you need to if you've got it cut exactly right, then your SWR will be theoretically perfect. However, that assumes you always transmit on the exact same frequency. So what you want to do is determine what range of frequencies you're going to operate on, and then cut it for like the middle of that range. So your SWR will vary as you get away from that center frequency, and we have a term for that called SWR bandwidth. Um, so and frankly, it can be pretty far off and still work fine. If you have an SWR of 2 to 1, that's fine. You're going to get out and talk just as far as if it was 1.1 to 1. People, again, you can overthink it and overstress things that don't matter that much. But you can't be like parts of a wavelength. If you're a tenth of a wavelength off, that's fine. If you're a half of a wavelength off, that's really bad because you're completely out of the band. Well, I mean, with some caveats about that. So usually what we do is figure out what range of frequencies you want to use. Like say you want to use the phone part of the 20-meter band and pick the middle of that and build the antenna for that frequency. We all generally make it a little bit longer than it needs to be and then put an antenna analyzer on it and shorten it down till it gives the best SWR. If you make it too short, then it's complicated because now you have to add wire, and so now you're out there soldering or something to make it longer. So you can't cut it longer. You can always cut it shorter, but it's a cut. It's a cut and try method. You know, you build it, measure it. How does it work? And then you tweak it a little bit.
Hey, Tom, let me ask you a quick question on
Sure.
transceiver purchase. I mean, are transceivers designed around certain frequency bands and then you make an antenna for that frequency band, or do transceivers have more variability in them than that? And I say this out of ignorance because I haven't actually looked into what transceivers are on the market.
Yeah. So today's modern transceivers cover at a minimum all of the HF bands. Well, you can get, there's too many answers to this, so let me hold up before I commit myself to something. You, let's just say an HF transceiver, because you can get a VHF transceiver, and that might cover 2 meters, 70 centimeters, and possibly 6 meters. Typically, they're more high end. An HF transceiver will do from 160 meters up to 10 meters and maybe 6 meters. I have an ICOM here which does 6 meters, but not 2 meters. And there's another ICOM IC7000 which actually goes up to 2 meters as well. So the generalized answer is most modern transceivers cover many bands. And now you have to figure out how you want to design antennas for that. Just take again in very general numbers, 20 meters and 40 meters. Okay, the 40 meter, based on the math, a 40 meter antenna is going to be twice as long as a 20 meter antenna. So how do you handle that? Well, you might build two antennas. I know people do that. They put one up there for 40 and one for 20. Or you might do something with something called traps in the antenna, which allows it to work on both bands. And you can get more exotic designs that will serve multiple bands. I have an antenna up on my tower outside, which covers 3 bands. I can use it on the 10 meter, the 15 meter, and the 20 meter band. If I want to go to 40 meters and 80 meters, I have to switch to a different antenna. So I hope that kind of gives you a generalized answer. Typically, your transceivers cover multiple bands, and you would either have an antenna that works on several bands, or you would have multiple antennas. And by the way, why do you do that? Well, now you're in the propagation situation. At night, 40 meters works much better than it does in the daytime and over longer distances, whereas 20 might not work so well at night. So when I first started out, and it was at a kind of the low, not the peak, not the bottom, in between on the sunspots, I used 20 meters during the daytime and 40 meters at nighttime, because of the situation with propagation. So in fact, I had an antenna that could work on both bands using something called traps, and you'll learn all about this when we study the general.
Okay,
They
admittedly, it's a
also
little
have
more.
let me add one more point. So you might be operating on with a tech license, you'll be typically operating on the 2 meter and the 70 centimeter band, and they make antennas that work on both of those bands. And so you could design your own antenna and cut and make 2 different antennas, but there's antennas that are out there that are designed to work on both, and you don't have to worry about switching or be concerned about it. The little Baofeng HTs that we talk about, some people have asked me, that's got a little rubber ducky antenna on top, and I like to say it works equally poorly on both bands. But you typically, with those little small radios or even a mobile in your car, you just have one antenna for both. Great questions. there's two things. One is what we always say is join a club and start working with other hams, and they'll show you their stuff and how they do it, and catalogs and websites and everything else, and you start, really learning it by hanging out with other people. The other thing is in the spring we'll do some seminars on different operating practices and techniques, and we'll cover some of this, like how to buy a radio, what kind of things should you look for, um, what what antenna construction possibilities are there. And then, everybody's got what people ask me, what's the best antenna? I said, well, where do you live? How much money do you have? What kind of operating do you want to do? Those are all factors that get into it. If you live in a place where there's restrictions on putting up antennas, then you might have a really thin, almost invisible wire up in the trees that nobody can see. Whereas at my house, where nobody cares, I've got like a 60-foot tower with a beam on top of it. So, and everybody comes out and looks at how car can you talk on that thing? So, so those are all factors that enter into it.
More complicated than I thought.
It's a lot of fun though. It's like it wouldn't be fun if all you did was take something out of the box and hook it up and talk on it.
Yeah, there's some convenience in that.
Well, it works both ways. But if you join a club and they have a great ham station like we have at the museum, then you don't have to think about any of that.
If anyone else has get an Elmer.
Yeah, so in ham jargon, an Elmer is a mentor. And I guess it all started back when there were two hams and one was helping the other, and his name was Elmer. But that's the ham jargon for somebody who's helping you. A guy with a person, I shouldn't say guy, an individual with more experience and who's helping you. And there's a verb for that too. It's called Elmering. So we say, yeah, I'm Elmering so and so. All right. Well, I'm as always, I'm way over time, but thank you for your attention. Hopefully, this helps you get through the exam. By the way, I guess those of you who've passed the test, congratulations, but you can't get your license because the FCC's closed down. Hopefully, they'll resolve that pretty soon. You guys can get into the swing of things. All right, I'm going to call it a night. Thank you all. Let me stop the recording.